All right, this is the last part of section 11.3. We're going to describe regions with polar inequalities. So here's how this works. I always start with a little line emanating from the origin, and where it enters the region is where R starts, and where it leaves the region is where R ends. Now, if the region is shaded right up to the origin, R is going to start at 0. Now, where does R leave? Well, R leaves on this line, which is the line x equals 1 over root 2. But we need to express that in terms of polar coordinates. So to x equals 1 over pi over root 2 is R equals, I said that wrong, x equals 1 over root 2 is R equals 1 over root 2 secant theta. And to get that, if you've forgotten how from the last video, replace x with r cos theta and solve for r. R is 1 over root 2 secant theta. So that's where we leave. Then theta goes between, and you can usually do the theta by inspection. If the region is shaded right up to the positive x-axis, theta is starting at 0. And I have that shaded region. I have these lines emanating from the origin right up to this point, which is a line, and a point on that line is 1 over root 2, 1 over root 2. So this must be the line y equals x. And so that must be the angle pi over 4. And those are the polar inequalities that describe that region. All right, let's do another one. Again, we start with a little line emanating from the origin. That line is going to start at 0, and it's leaving at the line y equals root 3 over 2. Convert that to polar coordinates. Replace the y with r sine theta and solve for r to get root 3 over 2 cosecant theta. So that's the line r equals root 3 over 2 cosecant theta. Horizontal lines will be cosecant, vertical lines will be secant. Then for theta, theta is not starting at 0 here because we don't have those lines until we hit this point. Well, what angle does this point correspond to? You can just do it in your head, or you can say, well, tangent theta is y over x. That simplifies to tangent theta is root 3. And so theta is going to be pi over 3. And then you can just do this angle visually. This is clearly pi over 2. So those are our limits on theta. All right, so you know how this works. Pause it and you try these 3. All right, I hope you did that. For the next one, this is not a, so again, start with a little line emanating from the origin. The line, the shaded region starts at r equals 0, and it leaves not on a vertical line or a horizontal line, but on this circle. It's a piece of a circle, and the circle is of radius 2. So that's r going from 0 to 2, because the polar equation for a circle of radius 2 centered at the origin is r equals 2. Okay, then for theta, theta starts at 0, and it goes to whatever this angle is, and a point on this line is 1 root 3, so tangent theta is root 3. So again, this is the angle pi over 3. All right, x1, draw a little dotted line emanating from the origin. R is going to go between 0 and the line y equals 6, which is R equals 6 cosecant theta. And then theta isn't going to start until you get to this angle, which corresponds to pi over 4, and it ends at this angle, which is pi over 2. And finally, you might say, well, does R always start at 0? And this example is good because it illustrates no, R doesn't always start at 0. So let's take a little line starting at the origin, emanating out. The beginning value of R is when that line enters the shaded region. So that line doesn't enter the shaded region until this circular arc, R equal 2. So that's our beginning value of R. That line leaves the region on the vertical line, x equals 2. Let's rewrite that in polar coordinates. That's R equals 2 secant theta. So 2 secant theta goes here. And then theta is going to start, we've got shaded region down here starting at the origin all the way up to this angle. So that's 0, and then this is the line y equals x, so this is the angle pi over 4. So this is going to be really important when you get to Calc 3, because we're going to be integrating over these regions, and these values you're finding here are going to be the limits of integration on a double or triple integral. So I'm not just doing this because it's fun, it is fun, but I'm doing it because we're going to need it next semester. All right, I've got some problems here for you to do at home with solutions at the end. This one's interesting because to describe it with polar inequalities requires 2 sets. You're going to have one set for the region underneath the red dotted line and one set for the region above the dotted line. And that's because, depending on what theta is, R is going to leave at a different line. So here, for this lower region, R is leaving at the line x equals 3 root 3. But for the upper region, R is leaving on the line y equals 3. So you're going to need separate sets of equations depending on what theta is. And then there's a review problem of just basic parametric curves, eliminating the parameter, and then using your parametrization Bible to parameterize curves. And the solutions are at the end.